6. A student takes a 20-question true-false exam and guesses on each question. Find the probability of getting 60% or higher on the exam. And would you consider this event to be likely? Is this a likely event to occur? Pause it, see if you can go through the whole problem. I mean, every one of these problems are a little bit different, right? Again, if you focus on getting the N, the P, and the X, I think you'll help yourself out. Okay, welcome back. I know you paused it. If you haven't, pause it. See if you can get these to come out. At least mentally go through the exercise. Don't wait for me to tell you. 20-question true-false exam. So 20 questions. There's my N. The probability on true-false, so getting them right, is what? 50%. 0.5. We want the probability of getting 60% or higher on the exam. So what am I looking for? I'm looking for X, so 60% of what? 60% of 20. So how many would I have to get 60%? So I need to find here 60% of 20, 0.6 times 20. Hopefully this is not too bad for you. You get 12. So I could have asked the same question and said, what's find the probability of getting 12 or higher? So let's crunch this out. So binomial, or distribution, go into binomial PDF. I'm looking for one value, 20, comma, 0.5, comma, 12. 0.12. So would you consider this event likely? So we have about which this transfers into about a 12% chance of getting it. Not likely, but not unlikely. 12%. I mean, that's greater than 10%. So I mean, it's not super rare. What if I had said find the probability of getting 90%? Oh, wait a second. I messed this one up, didn't I? It says 60% or higher. I missed that. I bet some of you caught that. I'm screaming at the screen. 60% or higher. So what does that mean? 12, 13, 14, all the way up to 20, right? So I've got to do some adding here, or I can use CDF. We'll do it both ways. Even the master makes mistakes every once in a while, so let's go ahead and... I'm being sarcastic. I'm not a master. Let's go ahead and do this binomial PDF. I'll do the PDF way first. So again, 20, comma, 0.5, comma, and here's where we're going to put a bunch of them in. 12, comma, 13, comma, 14, 15, 16, 17, 18, 19. So not too bad. There we go. Let's store this list into L1. I would not want to have to add these up by hand, so let's store this. Store. Pop that into L1. Press enter. Okay, so let's go back and look at that list, make sure they're in there. Looks like they are in L1. So now stat, scroll to calc, one variable statistic, and just pre-emphasize L1. So the sum is... That is wrong, or we know. So the sum here is going to be 0.2517, or 25, about 25%. So would you consider this event likely? Yeah, it's not that unlikely, right? So I'm not sure if I'd say it's likely, but it's not unlikely. I wouldn't be surprised of getting that. So, what's our threshold? Our threshold is usually about 5%, right? So if we're that's sort of common in the statistical community. If it's less than 5% chance, it's unlikely or rare. If it's more than that, it's not unlikely. So just kind of keep that in mind. Let me show you how to do this with the CDF. Okay. Again, think of what we're doing. 1 through 20. So just picture 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13, 14, let's move this out of the way. 15, 16, 17, 18, 19. Barely got it on there, 20. Okay, hopefully you can make out these other ones. Okay, so what are we trying to find? We're trying to find 12 all the way through 20. So what could we do? We could find all the way, oop, left off my 0. Could get 0 right. So I could find all of these from here to here, subtracted from 1. If I total all this up, what's that total going to be? That's going to sum to 1, right? So the sum of all of these is going to be 1, just from the nature of the probability distribution, right? So if I found this one right here, if I find this probability, I can subtract it from 1 and get this over here. So I find that by going to distribution, binomial CDF, and then, oh, we're not back on 30, we're on 20. So 20, comma, 0.5, comma, we're wanting 11. So again, that is this probability. So that's 0.7483. So I'm looking for this probability over here. This probability plus this one equals 1. So I just subtract 1 from that. So I just do 1 minus that. So 1 minus ands 0.2517. The same thing I got before. Once you see that, it's not too bad. But I know it's hard to see in the beginning, even after 3 or 4. But I really want to encourage you to try to get them that way. Now let's look at the mean and standard deviation of the binomial random variable. Standard deviation. Okay, so the mean is n times p. Hopefully this sort of makes sense. So let's say I have a 20-question true-false test. 20-question true-false test. What's the mean can also be thought of as the expected value. What's sort of expected if I were just guessing that I would get on this, if I just knew nothing? Because what's the probability here? It's 0.5, right, for each one. This is my n. It'd be half of that, right? 10. How do I get that? Just n, 20 times 0.5 to get 10. So that is my mean. So hopefully that formula just sort of makes sense to you. You just take the n times the probability. If I'm a 30% foul shooter, pretty bad, that's probably about what I am, and I shoot 10 free throws, I'm getting ready to shoot 10, what would you expect that I get it right? Like that I get in the hoop? 3. 30% of 10 is 3. 0.3 times 10 is 3. Standard deviation and variance are a little bit harder to conceptualize where we get this, just kind of accept it. Q is 1 minus P. Okay. So definite note card material if you don't have those in your head. Okay, a couple more examples. 3% of calculators are defective. Find the mean, variance, and standard deviation of a lot of 300 calculators. Okay, so what would the mean be? Again, the mean is n times p. So let's label this. What is n? So n is 300. And what is p? 3% are defective. So we want to, that's kind of our success, right? In a weird way. We want to know about defective. So to find the mean, it's going to be 300 times p, 0.03. And what do we get when we multiply that? We get 9. Okay, so if we select a lot of 300, sort of our expectation is we get 9. This is the mean. If I were to select this sort of sample lot of 300 each time, we would expect 9 to be the number that we get. But we may not get 9. We may get 7, 8, 9, 10, 11, 12, so forth. But the mean is 9. Standard deviation. Let's do variance first. So what's the variance? Again, n times p times q. which is n times p times 1 minus p. So in our problem, it's going to be 300 times p, which is 0.03, times 1 minus p. I'll put that in there, but you can probably do that in your head. So we get, whoop. So 300 times 0.03 times 0.97. And so this is where you need the calculator. Probably not one you can do in your head. So we have 300 times 0.03 times 0.97. And we get 8.73. Actually, should have a little square there, right? Thought I had it on there, but sometimes the pen does not register. So this is my variance. So what's standard deviation? It's the square root of that. So don't compute it all again, just take the square root of that number. On the calculator, you just press second x squared and then pull that answer back up by pressing second and the minus key. That ands will kind of pull back in memory the last thing that it evaluated. 2.95. Okay. See if you can do this one on your own. So find the mean, variance, standard deviation for the number of heads when 20 coins are tossed. Okay, welcome back. So the mean, hopefully this is clear, right? We have n is 20. Probability I get a head is what? 0.5. Half are heads, half are tails. So I mean, it's the probability of me getting a head is a half, probably getting tails a half. So again, the mean is n times p. 20 times 0.5, 10. How about the variance? There, square, stuck that time. np cubed. Again, n is 20, p is 0.5, q is also 0.5. 1 minus p. 1 minus 0.5 is 0.5. So we just do 20 times 0.5 times 0.5. We get 5. My calculator is still rounding to 4 decimal places, so maybe I should go ahead and take that off. Float. Notice I just get 5. And so what is the standard deviation? It's going to be the square root of that variance. Square root of 5, which is, I think, what, about 2.2? So the square root of 5. So 2.24. So again, we have the mean, 10, variance at 5, standard deviation, 2.24, square root of 5. Okay, another one. Suppose you take 20 question multiple choice tests with 4 choices for each question, find the mean, standard deviation, variance. Okay, so again, hopefully we're getting quicker at this. So n is 20. What's p going to be if I've got 4 choices for each question? 0.25. Hopefully that makes sense. Find the mean. So the mean is n times p, or 20 times 0.25. You get 5. That kind of makes sense, right? I mean, if you take a 20 question test, 4 choices for each question, you have no idea what's going on, you kind of expect to get 5 of them right? Just on average, if you were just kind of guessing. Okay, the variance, again, is n p q. So again, it's going to be n, and again, this is n p times 1 minus p. And I'll often just do this part here in my head. So n is 20 times p is 0.25 times 1 minus p is what? 0.75. So let's multiply that out. 20 times 0.25 times 0.75. And we get 3.75. So standard deviation is going to be the square root of that. So the square root of that prior answer. And we get about 1.94. Okay, so not too bad. I mean, if you can identify N and P, the formulas are relatively easy to crunch in. Okay, last one, I think. See if you can read through this one and answer the questions here. All right, welcome back. Clinical trial Lipitor, a common drug used to lower cholesterol. 863 patients were given a treatment of 10 milligram tablet of Lipitor. That group contained 19 patients who experienced flu symptoms based on data from Pfizer. The probability of flu symptoms for a person not receiving the treatment is 0.019. So assuming Lipitor has no effect on flu symptoms, find the mean and standard deviation for the number of people in groups of 863 that can be expected to have flu symptoms. Okay. So, assuming Lipitor has no effect on flu symptoms, we would expect from 863 and 0.019 of those to, want a number? Oh, finding the mean standard deviation. So there's our probability right there. So again, N is 863, P is 0.019. I cannot do that in my head, so I'm going to crack out the calculator. 863 times 0.019. So about 16 of them. So the mean is about, we'll say 16.4. And standard deviation is again square root of NPQ. So we'll just do that as all on here. So the square root gives me an open parentheses N, which is 863, times P, which is 0.019 times, and I can also just do 1 minus 0.019 here. Double close your paren, because I'm closing one for the subtraction and then the other one there. And so I get a standard deviation of about 4.01. So, based on the results in Part A, is it unusual to find that among 863 people there are 19 who experience flu symptoms? No, not really, right? I mean, we can, we drew this out here on the bell curve. You know, if I just rounded to 16 and used 4, 20, and we'll just go down to 12 here. I mean, most of my data falls in here, so 68% fall in there. So having 19 right there, that's not that unusual. It's within 1 standard deviation of the mean. So not unusual at all. You know, if we found like 30, then that would be unusual, right? Technically, the area we're looking for here is this part right here. But that is definitely bigger than 5%. Remember, 5% was sort of the rule I gave you. If it's more than 5%, then we can consider it unusual. Okay. Based on the preceding results, do flu symptoms appear to be an adverse reaction that should be concern of those who use Lipitor? I'd say no. As it happens in the general population. Without any treatment, we get this much. The last thing we'll look at is constructing binomial probability histograms. So suppose you take a short 5-question multiple choice test, 4 choices per question. Let's create a binomial probability histogram, and we'll comment on the shape and distribution. Let's start here. So again, we're going to have n, p, and x. So n is 5, p, 5 question with 4 choices. We have to be given that. So p is 0.25. And we want all the values for x, right? So we're wanting this distribution here. So there's x, p of x. So we have a total, we can have 0, 1, 2, 3, 4, or 5, right? So I can have my calculator find those values. Distribution. And then go down to binomial. We'll do PDF because I want those individual values. So n is 5, comma, p, 0.25. And then I want to put all those values in. 0, comma, 1, comma, 2, 3, 4, comma, 5. And I'm going to store it this time in L2. And I'll show you why in a second. So let's pop this in L2. There they are. So if I go to stat, edit, so let me clear out L1. It's not in L1. I put all those in L2. So 0 is 0.24, 1 is 0.40, we'll say. 2 is 0.26. 3, let me just go ahead and put my values in here so I can keep up with that. So 0, 1, 2, 3, 4, 5. Right. So 3 is 0.08, 4, 0.01, and then 5 is really small, right? 0.00, 1 if I'm rounding. Okay. If I'm doing it by hand, I can just crank that out. Look at the highest numbers at 0.4. So make that 0.4. Half of that's 0.2. Half of that's 0.1, and so on. So 0 is 0.24, so a little bit above that. 0. 1 is at 0.4, so all the way up here. And then 2 is back down to 0.26, about right here. 3 is at 0.08, so almost at 0.1. 4, almost nothing. And 5 is just a little blip, right? So sketch it by hand, that's what it looked like. Now notice why I put it in L2, because now I can just do a histogram here, right? So there's my L1, there's my L2. I did this with an earlier lesson. I can turn on my histogram, so make sure a histogram's on, L1, L2, and then do a zoom 9. But that doesn't look good, does it? So I need to press window, make my adjustment to X scaling, make it 1. Look at your X max. 10 doesn't make any sense. I'm not sure why I even chose that. So I'm going to make that 0.5. I usually make it a little bit more than the highest value here. So 0.5. Sorry, not X max. What am I thinking of? I'm thinking of Y max. So X max is 5. It's Y max, not at 1.2. I was wondering where they got that big number. Make it 0.5. Then press graph. Looks pretty good, doesn't it? Kind of what we have. So we have press trace. There's our first one. There's our first one there, 0.23. We're at about 0.23. Just scroll over. 0.39. Here we're at about 0.40. And so on. 0.26. 0.08. Oop, I need to go one more, don't I? Let me change my window. I usually go one more than my max because that value will be, there's actually a value there. You can't see it on the histogram the way it's drawn. Again, trace. We can trace down. And there's that one there, really small. Again, we could adjust the Y min if we wanted to. Maybe make it -0.1. Maybe it'll get a little rise. Nope, we still can't see a rise. If that number is just, 1/1000th, just not going to show up. But it's there. Last one, I believe. Suppose you take a 20-question multiple choice test with 4 choices per question, create a binomial probability histogram, and comment on the shape of the distribution. Okay, so we're not going to do this one by hand. We'll just use a calculator. Okay, let me show you a kind of a slicker way to do this one. We have 20 values. I don't really want to have to plug all those in if I can help it. So, what if I had 100? And I don't want to put 100 numbers in. So let me show you kind of a slick way to do this. We have to go ahead and put in L1, we go ahead and put our 0 through 20. There is a way to automatically generate that, but I'll be honest, I'm not going to give you one with 100. 20 would probably be the biggest I would give you, unless we were using StatCrunch, and I'll show you how to do some of this on StatCrunch later on. What we do is we scroll over and scroll up to L2, because we want L2 to sort of become a function now. We want to actually impose a function on this L2. The function we want to pose is the binomial. So we want this thing to do a binomial, so second distribution. Go down to binomial PDF. We want individual values for these. And then just put in, notice it shows up binomial PDF, and notice it says L2 equals. Don't put it in the blank. If you're going to put it in the blank, it won't work. Binomial PDF, and then put our values. We have 20, comma, 0.25, and we don't have an X. Our X's are actually right here. And what it's going to do is it's automatically going to take what's in L1 for our X's. So just close the paren, and now press enter, and watch what happens. Isn't that beautiful? All those values right there. Let's scroll all the way down, and notice they're getting smaller and smaller and smaller and smaller as we get down to 20. Okay? Much quicker than doing it the other way. So now, and if you only have 3 or 4 values, probably not that much quicker, but with 20 values, it's definitely quicker. So let's go into our histogram. We get a second y equals. We make sure our histogram is on with L1, L2. It is. Press zoom 9. I don't know why it likes this right here. Maybe yours is doing a better job than mine. Go out and press window. X max. Not sure why it's choosing. Let me start back on a standard viewing window. Maybe I messed mine up somehow. Okay. So now let me do a zoom 9. No, still doesn't like it. So window X max, not going to be more than 20, so let's make it a little bit more, 21. X scaling is at 20? No way. I need to make X scaling 1. And what I did is I kind of glanced at that list in my stat menu. So let me go back here and show you. And you kind of see which one is the highest. Where's my highest value? Notice it starts low, it comes to a peak at about 0.2, and then comes back down. So that's going to help me with my window of my Y max. Let's make it a little bit more than 0.2. How about 0.25? Not that big a deal, and let's make this maybe negative 0.1. Well, look at that. Isn't that beautiful? If I trace, there's my 0 at 0.031, at 1 at 0.02, 0.06, 0.13, 0.18, and there's our peak at 5. And then we come back down. And you know, once we get past 11, I mean, you can't really see anything down there. There are values down there, but they're just so tiny, they don't even register on the calculator. If you did this on a computer, you may be able to register some of these, but not all of them. Okay, and so what sort of shape would we say this shape is? Say it's mound shaped, right? That's going to become important later on. We'll be using the normal distribution to sort of approximate our binomial. We can do that when we have, you know, a n bigger than 20 or 30, you know, a p that's not too small. There are some requirements we'll have you go through, but kind of start making those observations now.